So yeah, my name is Ramses Benson. I'm an analyst at SciNet, and at SciNet we host this cluster called Trillium. And it's not the only cluster in Canada that's available for academic research, but it's a little bit different. And so that's where what this colloquium is about, to not just explain what's different, because if it's just different, then we're just being annoying, but also why. So I'll start with the obvious sentiment that is very understandable. We want computational resources, and now you've got a large computation to do. You got your account in the CCDB, and you should just be able to do that and quickly too, and lots of it. But we all want that, so we're going to have to do a bit of thinking here. So there are a lot of computational demands from Canadian researchers or researchers in Canada. And one thing you might know is that the Digital Research Alliance of Canada, DRAC for short, has an annual competition for getting resource allocations. And so it depends on how much you need. If you only need a little bit, you don't need to apply. But if you have quite a bit of computations to do, you have to go through this research competition. And we just started the allocations for this year, so we call that 2026. Um, and the number of groups applying is enormous. It's almost 800 groups. They're all applying for resources, and if you add up what they all want, there's simply not enough. So not everybody can get what they want. We have just as all of Canada, of all of the alliance clusters, refreshed all our systems in the last year, and so there's much more available, and yet we could only satisfy about 90% of the CPU asks, so people that want to compute on CPUs, and 23% of the GPU asks, so people wanting to do GPU computing or AI, stuff like that. So the demand is greater than the supply. Now, that's not even taking into account that if you have small requests, and small requests are not that small, like less than 200 core years. The core year, think of it, you're constantly computing on 200 cores. That's not how it works. You don't just get that. But if it's less than that in your request, you don't even get an allocation. You just have to make do with what's left over after the allocation. Now, that's a fair bit and depends on the system. It's about 25% of the systems are used for what is called opportunistic allocations or default allocations. And so you can get a lot of work done at that scale even without an allocation. This is why it's not worth bothering. But so on top of that, we've got all of these other larger asks. So the moral of the story here is that there's more resources than requested than we have, and so we have to make sure that we somehow allocate it fairly, the usage is fairly, and there's still some leftover room for people that are just starting or trying things out or have relatively small requests, and it's relative small. It's still small. It's still not small. Right. So the whole premise here is that we as the let's say the host side and as the uh, organization maintaining the system or administering the system together with, of course, the Digital Research Alliance of Canada and all of its national teams, we have to make sure that the resources are well utilized, and that's true for all of the systems. And so that's the goal. That's the ultimate why we're doing things. The trouble is that not everybody's requirement is the same. So they don't all have the same computational characteristics. You could have projects that need very small computations, like little Lego blocks, but many of them. You might have some of those that have to run for a really long time, and that can be troublesome and hard to get. Some of them might use multiple cores, but still are okay with this, let's say a single node. So a node is a single computer basically inside the cluster, right? But if we're running on Trillium, we'll see that you always get a whole node at the minimum. That's 192 cores. So those are not small computations by themselves. But there's people that just need that. They don't have to grow any larger than that. But then there's also research groups that really need to go much larger than that. They need multiple nodes, so we're talking hundreds, thousands of cores running in parallel on the same computation. Um, so why is that an issue? And then some of them need large memory. And then some of them might need GPUs and others might not. So there's a real mix of requirements. One person's computation is very different from another person's, and how that all fits together in trying to make a system that is well utilized is the challenge, right? And in the end, this is a scheduling issue for the most part. It's like, okay, how do we um, put all of these computations together with a limited set of resources without wasting resources, but without also, but while being fair. By the way, James, if there's any questions in the chat, I can't see the chat because I'm in full screen. Just let me know, okay?
Yep, I'll let you know.
Okay, thanks. Okay, so that's what's the real issue here? The real issue is that if we just randomly start scheduling resources as users request them, our usage is going to look a little bit like this picture here. So we've got all kinds of different size of blocks. They're just more or less randomly thrown onto the compute nodes, but you might have uh, but it doesn't just naturally fit, right? So what actually happens is that our jobs on our systems are scheduled by a scheduler. The scheduler that we use is called Slurm, and this is what's called a priority queue. So when we are talking about allocations, those are not allocations. Those are not like computations like money in the bank that you can spend whenever you want. Based on this allocation number, you basically get a possible fraction of the system that you could use, or that's your target. And but you're not running full out all the time. And so that is actually translated into a priority. And so there's a queue, you submit a job, it goes in the queue, it's sorted by priority, and the algorithm behind that priority is aimed such that on average, you should roughly get the usage out of the system that corresponds to your allocation. But it's more of an average, and it's only working if you always have jobs in the queue. So you don't get an allocation, you get a priority. Okay. So understanding that, now we have a problem. So suppose we want to run large compute jobs, and that, as we will see, is what Trillium is for. What would they need? Well, they will need many nodes available and at the same time. This is one computation, so all these nodes have to be available at the same time. And preferably, they have to be somewhat close together. If they're working on the same problem, they're going to be communicating with one another. And so the closer you can be in a network, the better. Um, and then it's really it really only works if all of those nodes that you get in this large computation are essentially the same. So they run at the same speed. Otherwise, you'd get some nodes that are slow and all the other nodes are waiting for that. So you need a consistent hardware. You need a uniform or homogeneous set of nodes for that job. Now, if we allowed in the same system both small and large jobs, it could be hard to find these full nodes. So think of this picture here again, and think of this as three nodes, and time, I guess, runs from bottom up, and then there's a node, and here's a node. And each node has one, two, three, four, I guess, five cores here. I've got some serial jobs, some single core jobs here, and this is a particularly long one. I have to wait for this one to finish before I can start even a single full node job. And so there's a lot of wasted time here. Same here. So these small jobs would get in the way. And as this is a dynamic scheduling, as people put jobs in the queue and maybe they haven't used their fair share yet, they can get a high priority and they get put on a node. And so it can be a really long time before you can actually schedule these large jobs. Yeah. The only way to do that and make sure that these large jobs now run is to say, okay, we're going to prefer large jobs and we're going to hold some nodes until they're all idle, and then we'll start our job. And that works from a scheduling issue, but it means that all of these cores here are unused. And as we saw, we don't have enough resources, so that's a waste. We want to have as much utilization as possible. Yeah, so again, if imagine that you have one serial job on one of these nodes, the nodes have 192 cores. This one serial job is still busy for a week. All the 191 other cores would be unused until that time. Um, Now, could there be backfilling? Yes, there could be, but that is a limited feature, and it's not essentially fair either. So yeah, this is an issue. If you mix this too much, scheduling of the large jobs gets in the way, or makes the whole system very inefficient, or both. So how do we solve this? We have this wide variety of possible computations. Some people need very large jobs. Some people need many, many small jobs. Some people need a GPU. Some people do not. So first, do we really need, is this really a problem? You might ask, well, how many people are really running these really large jobs? Is it even worth it? Or is it such a small problem that, okay, we'll deal with it when it comes? And it turns out, yes. So you look at the rec applications and you will see that there is substantial demand for large parallel capabilities. They typically come from fields like aerospace, astrophysics, climate, nuclear physics, material science, engineering. There's some overlap between those terms, but yes, there's definite demand for large-scale simulation. So yes, this is not everybody, and if you look at the number of groups that are doing small things, you add them all up. Yes, they're substantial. There's a what I call a long tail of people that don't need large jobs, but there is also a substantial demand for these large parallel jobs that without those, they can't do their work. They can't do their nuclear physics. They can't do their astronomy. They can't do their engineering. So we do need this. Right. So the approach that was chosen, and this goes back to the previous generation of clusters. So those were then governed by Compute Canada. Now we have the DRAC. It's sort of a two-pronged approach. You make a whole, excuse me, a whole bunch of general purpose clusters. They're optimized for a variety of workloads, but nothing really large. And what is really large obviously depends. But and so those are your general purpose clusters, modest size, and again, modest size can still be hundreds of cores, but modest in comparison. And so those are the clusters for NIBI, Rorqual, and Narval that you might be familiar with. And then on top of that, there's one dedicated cluster for large parallel computations. In the past, there was Niagara, which was also at SciNet, and now it's Trillium, which is its successor. So the idea is put most of the stuff on the general purpose and make a cluster that is really good at running those large parallel jobs when you need them. And really good meaning both performance-wise, but also being able to schedule them in an efficient way. Okay, so if we want to do that, if we want to build a a cluster that can do that, sorry, um, what are the requirements? What should you build if you need a large system? Okay, so it's going to be dedicated to these large parallel jobs, um, and yeah. So it has to be good at computation, but also good at communication. Remember, or maybe you don't remember, but these clusters, so this is a picture of it. It's just racks. The racks have nodes in them. The nodes have multiple cores in them. So we have 192 cores per node, and then there's like, a few dozen nodes or many dozen nodes in a rack. They have to communicate to do their bigger jobs bigger than 192 cores, right? So you need that. So you need many cores. You need a good interconnect. So interconnect is what connects them. That's these wires here. And you will also need good storage. The bigger the problems that you are computing on, the larger their output or input is going to be. And they will have to write out their temporary and final results. And if that takes a long time, that's no good either. You're just waiting for the disks to do their stuff. Another thing that we found, although that is mildly shifting, is that a lot of these computations, and this comes straight from looking at what people are doing, a lot of the computations need CPUs mostly. There is work to port to GPUs, but there's still a large amount of work that needs to be done by CPUs, and sometimes that's just also the most efficient implementation. So we need quite a few CPUs, but we will also want GPUs. And then in the end, although this is going to be aimed at large jobs and schedule them well and have them run nicely, there's going to be people working both on this system and they will also have some work on the other systems because they have some, I guess, general purpose, smaller scale computations to do, or they might have moved from those smaller computations and now outgrown that and moved to Trillium. So, as much as possible, we do want to be compatible or similar to the other systems. And so, whatever changes there are, there has to be a reason for it. It has to serve the large parallel character of the system. But if we can, then we want them to be similar to the other systems. Um, so what does that mean? Well, first it means everything goes through the same set of accounts. So you've got your CCDB account, and that's where you ask for access to any of the clusters, but same for Trillium. Um, However, your folders are laid out in the other systems and how the permissions are. That should be very similar to ours. We will have the same software stack. Now, yes, there are different differences in architecture. So what part of the software stack uh, is uh, is appropriate to use might be different, but it's the same stack. You can write to the same CC support email, and we use the same kind of scheduler. So all of these systems use the Slurm scheduler. It should not be surprising, though, that because it's a specialized machine, there are certain things that you can and cannot ask for. We'll see those in a little while. Um, but the basic commands are all the same. So that's our sort of compatibility layer. And yeah. Okay, so let's look at the architecture difference first. So what does it mean to build a large parallel computer? And I've got a big table coming. Um, Here it is. Um, I could probably talk for a long time about this. The main point that I want to make from this table. So here I've got the architecture. So the CPU nodes that we have, the GPU nodes that we have, how much is each node have in local disk space, what the network is like, and all of these are kind of abbreviated. Um, we'll talk about blocking in a second then and the file system. So I've got all the major clusters here. And one thing you might see right away is they are actually remarkably similar. Um, the tweaks that you have to do to make a large parallel machine are really um, not qualitatively different. It's more quantitative. So we've got some clusters that have um, um, specific CPUs like Fur and Trillium have these Zen 5, which are AMD chips. Um, Nibby has still Intel cores. Narval has some older AMD cores. They have GPU nodes because almost all of these systems, except for Narval, are new. They all have pretty much the same generation of NVIDIA GPUs. They're all H100s, except for Narval, which has been around for a little longer, so they have H100s. The number of nodes that they have varies. So first, very much heavier on the GPUs. Trillium is a little lighter on the GPUs in terms of the number of nodes, right? That reflects this idea that we have a lot of CPU usage still. Although if you count the floating point operations per second, the CPU and GPU are pretty much on par, more or less. Not quite, but more or less. Um, so that's why people use the GPUs. They're powerful. Uh, yeah, so that there's not a lot of difference between what you put into each node. Um, One thing that is a choice in Trillium is that we chose to put no local disks in. Basically, that saves us money and electricity that we could put to putting more nodes in. And instead, or not quite instead, but we did make sure because there's no local disk that our file system is good. So we chose Vast, which has been fairly performant, but we're not the only system that has Fast. Like Nibi also has Fast. The other systems run Lustre, which when used properly is also fine. Fast is quite nice. We've had good experience with it. Another thing that does stand out is how fast your network is. So that's just those wires. How fast can they transmit bits. So our CPU nodes have 400 gigabits per second, the GPU ones have 800. So that's a bit on the fast side on purpose because remember the communication had to be really good. But then fur is also fairly large, so you go, okay, that maybe is there really a difference? And so now we're starting to see some other differences. So apart from the faster file system, or um, well, depends on how you measure that. In any case, how is this whole thing connected? How are the nodes connected? So we have 1,200 something nodes that have to be connected to one another. Um, they are not all connected to each other. There typically is like switches in the middle and stuff like that. So there's some topology. But you could ask, how many connections can I make from one node to another without them getting interference? So that's sort of the blocking factor. And on purpose in Trillium, every node can communicate with every other node at full speed. So the speed that you get here is not shared among um, connections. And so that means that if you did run a full 1224 node computation and those nodes have to communicate, there's no cost. They don't have to wait for one another, even if the communication is large. Whereas on other systems which aren't meant for that large computation, there is a blocking factor. That is to say, if all of the nodes are communicating at the same time, say in NIBI, you theoretically get half the speed. Networks work a little bit more complicated than that, but think of it that way. Narval has some have very peculiar ratios of what the blocking factor is, and it comes on in from how many lines go in and how many go out and stuff like that. The topology gets in there. Now, that's that blocking factor that I put here. And by the way, all of this is just I just took it from the docs site from Alliance Scan. So if there's anything inaccurate, it's we have to fix that. Um, The yes, so this is sort of the maximum blocking factor, but at a smaller scale, you can imagine that some nodes might be close together and nicely connected, whereas nodes further apart might have to hop through a switch and therefore get more blocking. And that is true for some of the systems. So, for instance, on Rockwell and Narval, up to a certain number of nodes, you can still get essentially non-blocking communication. So there is a certain amount of large compute that you could do on these systems. Whereas on the more general purpose side of for a NIBI, there's probably less blocking when it's closer. I'm not quite sure. There's still switches and stuff, but essentially, if you're past one node, you should not count on any one-to-one non-blocking communication. So the point of this slide is really, okay, so yes, the hardware is very similar, which is really nice. It means that something that compiled on, say, Fur will compile on Trillium, and it's just a matter of, okay, now we're scaling up, and we make sure our network is fast and well connected, and that our file system is performant, and we're always keeping an eye on that one. Right. So most of these are probably obvious improvements, but keep in mind no local disk. So if you're set up such that you're doing a lot of IOPS, a lot of IO operations per second, the standard thing to say to make that work out better for your jobs is to run on a local disk. We don't have that. Um, you could potentially then, if that is your workflow, and you are not running out of memory, you could use RAM disk. So that's like a disk that lives in RAM. It's not a real disk. And that's very fast too. And much like a local disk, you don't see it from the other nodes. It's sort of gone after your job goes. So that could be helpful. Now, if you're already out of memory, then you're out of luck. So you're going to have to make a trade-off. Not a lot of people need the local disk, by the way. That's another reason why they are not in there. There's very little demand. It comes in handy for some cases, but we haven't seen those cases where we couldn't uh, make do with RAM disk. Finally, because these are newer nodes, so the Zen 5 AMD chips are a bit newer, there are some things in the old standard modules, standard environments that may not work. Um, and that could be either an oversight or just it's newer hardware and the program doesn't know about it. So that can happen. And so we've hidden this environment because we are, no, it's new. And so you should use the standard environment 2023. You might occasionally find that there's modules that aren't in 2023 yet and that are in 2020. the best thing to do is to ask for us to reinstall them in 2023 to make sure that they work because 2022 is too long ago. So basically, um, we're not fixing it. We're just moving on to the next one. And in fact, you could sort of feel that maybe in the not so distant future there'd be a newer standard environment still, but um, this one will continue to work for now. Okay. So those are two things to keep in mind. You're working on Trillium, you come from another machine, use the modern standard environment and don't use local disk. And other than that, in theory, it should work in terms of the hardware. Are there any questions? I've
There's
put
no
the
questions
slides
in the
on.
chat.
No questions? Okay. I put the slides up uh, on our Moodle in if people want to look at it later, um, just in case. Okay, so that's the hardware, and the hardware is not the biggest deal, because the trouble was really in the scheduling. So the usage differences, which is what we're going to look at yet next, are uh, the biggest impact in a sense, right? Now we start fairly simple. You want to log in. Some systems still accept passwords. Passwords getting a bad rep for a good reason. So on Trillium, you have to use SSH keys and MFA, so multi-factor authentication. MFA is everywhere. The SSH keys are just an extra security layer, which I think Killarney does as well. We haven't even talked about those. Anyway, then there are separate login nodes for the GPUs and the CPUs. So to some extent, Trillium is two clusters. Um, because we want the jobs to run on as homogeneous a system as possible, all the CPU nodes are the same and all the GPU nodes are the same, but they are not the same among themselves. So in terms of scheduling, it helps to think of one of them as just pure CPU cluster. We call that Trillium, and one GPU cluster, which from the external point of view is called Tritium-GPU. But internally, you might see the term Grillium appear, so Trillium with a G. Um, yeah. So because they're separate, you log into the CPU part of it separately from how you would log into the GPU part of it. And then similarly, if you want to submit a CPU only job, you should do it on the CPU login node. If you want to submit a GPU node, a CPU job, you have to submit it from a GPU login node. So these two subclusters, as we tend to call them, each have their own scheduler, so you can't submit from one side to the other side. They are separate. That allows for certain um, optimizations that we can do in terms of the scheduling. Right, so the login nodes are the submission nodes, so you log into one or the other. By the way, I didn't mention it here, but the GPU login node has GPUs in it. So if you're compiling something on the GPU login node that uses GPUs and you want to run a short test, you can do it right there. And it'll grab that one of the GPUs and just run it. And for testing, that is very useful. You're not supposed to run large jobs on the login nodes. That's true everywhere. We've got compute node for that. Anyway, so the login nodes, those separate ones, are also the job submission nodes. Here comes a big issue here for people doing large or little jobs. The CPU resources are all scheduled by whole node, and the nodes have 192 cores in them. So if your workflow before was submitting a whole bunch of small jobs, even if you have hundreds of them, and you now try to do that on Trillium, if you submitted them in the same way, with the same sort of SBatch job scripts, you'd get a whole node that is running a single core. That's bad. We will find you if you're doing that too much, and we'll ask you to change your ways. So you have to get a whole node and then make sure you use those cores. The GPU resources are quite heavy. There's 4 GPUs per node. Um, I guess we could think about also scheduling them by whole node. There are just not a lot of applications that can use 4 chunky H100 GPUs for the same computation and actually get some usage out of it, a good efficiency. So we're scheduling those by GPU. So you always get a whole GPU, or really the way we've done it is we said, okay, there's four GPUs in a GPU node. We're essentially carving that in four. You get a quarter of a node. So you schedule by quarter node. Or by whole node. You can also get whole nodes, and then you get your four. So some people really have those large jobs where they use multiple nodes. Each node uses the four GPUs, and they do a decent job with that. But a lot of people just need a single GPU. Now, the other systems also subdivide their GPUs further because, as I said, the H100s are pretty beefy, and using all of it at the same time is tricky to use efficiently. So they subdivide it. It's called MIG. Uh, Forgot what it stands for. We don't have that. Right? At the end of the day, Trillium is meant for large computations. If it can't use a whole H100 GPU, then you can run on the other systems. They are there. That's fine. Um, Right. So GPU resources by GPU, CPU resources by node, and then we have a strict 24-hour limit on jobs. Um, we sort of have to. There's no because if we allowed for longer jobs, then either that node or that GPU would just be sitting there for a long time, and we would have a large job waiting for that node to become available. And so we again have bad utilization. We have unused resources that are being kept for many days just because this one job needed to run longer. What all jobs should do is to use a thing called checkpointing. It's better for your job, it's safer for your jobs. If something goes wrong in your job and you write out temporary data from which you can restart later, if you set your computation up that way, and a lot of applications can do that already, then anything happens within even the 24 hours, a power outage, you run out of disk space, whatever might, there's an error in your code, you still have a whole bunch of your computation saved. So it really is a safety issue. But it also means that if there is a large job coming in and it has priority because that group hasn't used much yet, then they can almost be certain that their job will run within 24 hours because within that 24 hours, enough nodes will have finished their job and this thing can run.
There's a
So
few
that,
questions, Ramses, in
yeah,
the chat.
right.
The first one is, are the nodes connected to the internet?
That's like I think the next box, but no, the nodes cannot contact the internet. We can make, yeah, there's ways to make it happen a little bit if you have like a license server to contact or something, but don't count on that. You can't download if you have any data that you have to download, you have to download it first before you start your job.
The next question is, can I submit new jobs on the compute node?
You can, but not by default. You'd have to basically SSH to the login node and then submit it again. So you need that trick, and it's a safeguard for not having what is it, exponential explosion of jobs. It's easy to write a job that submit two other jobs, that then submit two other jobs, that then so we want you to be very deliberate in this. So submitting a job from another job is very common if, say, you have a job that ran for, say, it's 24 hours, probably a little less to be safe, and then at the end of the job, it submits the next job. And that is one way to go. And for that, so yeah, we have tricks on the wiki on how to do that. You just SSH, try login 01, sbatch, and then your script again.
And the last question, are there any plans to implement an update for modules in standard environments? Or are there ways around running a newer version of a software module on a node?
Right. So, yes, there are plans, but they're not terrible. Well, they're plans, but they don't have an ETA. So, um, the hope is to have a 2026-ish stack, but it might happen depending on how busy people are towards the end of 2026, as I understand it. I'm not solely responsible. Now, this stack is shared among all the systems, so that's nice. Once it's there, it's here. But yeah, so there are plans. In the meantime, if you really need a piece of newer module, you can send an email to I guess you'd send it to support at tech.alliance.ca requesting this newer module. And if it's something that is of general use, it will get installed. But there's a bit of a backlog. So in that request, also say how urgent it is and whether you could not work with an older version.
And the last question, are interactive jobs scheduled by whole node 2?
I will get to interactive jobs. So the question is yes and no, or the answer is yes and no, but I'll get to that a little bit more later.
There's no more questions.
Oh, good. Okay. Right. So the last thing about the job scheduling is that you don't have to specify, you should specify how much memory you get. So if you're scheduled by whole node, what's the point in asking for less memory than the node has? You just get all the memory. So that part, I guess, makes sense. With GPUs, we could have done memory requests, but instead, what we decided to do, usually GPU processes, GPU computations, they're just limited by how much memory the GPU has. The CPU has more than that, and so that sort of it's not much of a point for most cases. So you just get a quarter of the memory. If you ask for one GPU, you get a quarter of the number of GPUs, one GPU, you get a quarter of the memory. That's sort of it. Okay, so interactive jobs. So we have a way to get an interactive job. The best way to do so is to use a special command that we made called debug job. You can use salloc, but then you go into the queue and you might be making debug has a few nodes that it can get quicker access to. It's set up to have a limited time, 1 hour. So really it's just for trying things out or for debugging things. That's why it's called debug job. But really nicely, and I think that is unique to Trillium, is whatever you do in a debug job does not count to your fair share. So you can't blow through your fair share because you left your debug job running. We You can only have one at a time, so it's hard to abuse it. But that one doesn't count to anything, and you almost always get it within a minute or so. So it's really nice. But it still is um, a real compute node. So you get a full compute node or a quarter compute node for the GPUs. That is still a whole node. The idea is that this is going to be your test bed. There's no other users for that resource. You can see how things are performing. You can try things out. If they crash, you will see it right away. You can try again, so it's interactive and useful. But it is still scheduled in the same way as the other ones, but doesn't cost you anything. Let's go here. Right. Okay, so that there's a few more usage differences. Um, Home, we've made home read only when you're doing compute nodes. Some applications really like to write to home, and we can help you um, tweak that. But in essence, home is a backed up piece of storage. It's your most dearest files are in there. And so we don't want to run the risk of it overwriting it. And we also don't want the risk of the backup system being so busy because you write to home all the time that it doesn't actually manage to back up home. Right? So this is an optimization and a safety feature. We gave you a little bit more space, I think, on Trillium than other systems. I think you get 100 gigabytes instead of 50 gigabytes, and you can have 1 million files. Again, this 1 million files is there because if we give you too many files, basically our backup can't keep up. And so what it means that instead of having a nice, safe backed up space, you have a nice but not safe backed up space. So you delete something, that's too bad. So that those are restrictions to home. Home shouldn't be for active data anyway. So that's yeah. Project. Everybody gets some projects. If you came from Niagara before, like a year and a half ago, not everybody got a project space. You get a project now. And you might have several projects, and so we've put links to those several projects that you might have access to into a subdirectory in your home directory called links. And so that's where you will find all those project spaces. And those are shared spaces between the members of the group of that project. The home is private, like on all the other systems. Yeah, so default accounts still have access to a project space of 1 terabyte. We can't increase that. We don't have enough space to give everybody a bump up to 10 terabytes, or 40 terabytes, which you can have on the general purpose cluster. So if you really need more project space than that, you have to request it through not yeah through the resource allocation process. Okay. And then we did something that took a second for people to get used to, but they seem to have figured it out. We also made project read-only from compute nodes. So you're not supposed to write your data into project from your computations. They're supposed to go to Scratch, which is the next box. Um, and the idea is kind of the same. We want to protect project, um, and we want to be able to back it up sincerely. So there'll also be limits to the number of files and the spaces, but it depends on your allocation. But yeah, the same reasons why home is read-only, project is also supposed to be special, but it's shared among the group. So where home is sort of yours, project is data that doesn't change a lot um, and is shared within the group. For your writing inside of your jobs, you need Scratch. So again, Scratch is per user, and nominally you have a quota of 25 terabytes. You cannot all use it because it would run out. That's sort of an upper limit. You're supposed to clean up. And once you're done with a job and there's some data that you need, you can move it over either on a login node, a data mover, or using Globus. There's different options to a project if that needs to be kept and shared with the rest of the group. We don't purge yet. Um, we don't need to yet. That's really the real reason. And so we'll come up with a purging policy at some point in the future. But for now, anything you put in Scratch is still going to be there. And then another space that the other systems have called nearline works differently on Trillium. So what nearline is it's for storing data that needs to be stored for a little longer. Imagine that Scratch was, say, purged every 2 months or something. You want to keep it for longer, like, in about 6 months or a year, you're going to need it back. But you don't need it right now for running your jobs. You will want to put it somewhere where it's safe, but doesn't take any space. And that's tape. You want to put it on tape. So Nearline is a tape-backed storage system for longer term storage. So the way that it's implemented in Trillium is through a system called HPSS. In fact, that system predates before we started calling this Nearline. So we just call it HPSS. That's its name. It's a high performance storage system. But it works through fairly explicit job scripts where you say, I want this data to be moved over there. And so that's a very different way. It's not a file system. So it's not mounted as a file system on Trillium. And so you should not think of it as that. So you won't find a slash nearline. You might have space on it, but you'd have to look up the HPSS documentation to see how to put it there or to get it back from there. It's not terribly complicated, but it is very different.
There's a couple more questions in the chat.
Mhm.
We have one. When running a Python job using matplotlib, the library attempts to create a .matplotlib configuration directory in home. Since the directory is read-only, this triggers warnings. What is the best way to redirect this path or suppress these warnings?
So for matplotlib, I think there's actually an environment variable that you can set. I wouldn't know from the top of my head which one it is, but that's one. Another thing we frequently do when there isn't such a mechanism is to put a soft link from what looks like a directory in home, but it's just a soft link to project. The only downside now is that stuff isn't backed up. But if it's just data that you didn't know was going to be written anyway, do you really care? You probably don't care. So those are the two main ways we get around it. Either there's an environment variable that the documentation says, and then you can write to that, and there's no issues. You get rid of the warnings. Sometimes the warnings don't matter. Sometimes the warning says, and Matplotlib might be doing that. It says, okay, I'm going to use /temp or something like that. That might work fine, but then you have your warning. And then the other workaround is this soft link mechanism that you might need.
And the next question is, for data compression, does the post-run data processing / compression within the compute node only compile data into Scratch only? i.e., attempting to transfer compressed data into project within the job script.
Oh, I see. I think I see. So the idea is that you produce some data, and at the end you want to compress it, tar it up, zip it up, and put it into a project. Um, I guess technically you could do another SSH trick, but by and large you probably don't want to do that. You probably just want to do that either by hand or with some sort of automated job in on the login nodes. And the reason I'm saying that is that um, those kind of operations tend to be kind of serial. So imagine you have your 10 node computation, it ran for a few hours, and then you have one core in there chugging along for another 30 minutes to zip things up and stuff. So I would not do that. In fact, compressing tends to not, unless you really run out of space, compressing might not even be necessary. But yeah, that's so yeah, it's probably best if you can manage it to just do it on the login nodes, or we have data mover nodes as well if it's sort of heavier. Um, and although it's technically possible to do so from a job script, it's probably more fragile to do that. So I would try and avoid that. Any other questions?
That's it for the questions.
Okay. All right. So lots of little differences in how you set up, mostly in how you set up your computations. But a lot of it is the same. So your CCDB stuff, it works just the same way. That's how you get access. Your username that you have on your CCDB for the other systems is the same. You log in with SSH just as on the other systems. If you have SSH keys for Trillium or for Killarney or for they also work for all the other systems. So it's actually an additional security that you have for all the systems. The environment is the same. You've got Linux, you've got the same software modules, you've got a Slurm scheduler, so your basic stuff is very similar. You've got the same file system set up. They're all shared systems. You've got a home, you've got a scratch, you've got a project. Um, I think we do set an environment variable called $project for you. If you have only one project, that's going to be the one. Um, I think that might be unique to Trillium, but home and Scratch are set to your personal home and Scratch directory. Home and project are backed up. Scratch is not. If you want to do file transfer, you can do it through the login nodes or through the data mover nodes or through Globus, which it's all very similar to the other systems. We do have a nearline, it just works differently. Your group membership also is very similar, so that used to be different on Niagara. If you were a member of a group in another system, you're a member in that same group. Um, yeah. Uh, so one of the things that changed, for instance, that your home directory isn't shared with other people in your group because it's only part of your personal group. And well, I guess you could tweak that. It's probably you don't want to do that. It's extra private. Yeah, and then, so you have the same directory layout, same kind of permissions that we have on the other systems. So that's um, um, yeah. So if you figured out how to do sharing on the other clusters, it works the same on Trillium. Okay, so um, that's for the really large computations. This is why we have to tweak things a little bit. Some are security related, and most of them are just making sure that these large jobs can run and run well without wasting resources. Um, But that tends to be not the only thing in your workflow, right? Sometimes you either have to prepare your work, or you have you want to make some plots, or you have to do some interactive work. Um, what then? And so there's a few possibilities there. We already talked about the debug job, but if you're not ready to run your large jobs, you should test first. In fact, if you're just starting on Trillium, the first thing you should do is not submit a job. There's no way you know what's going on. Test it. So and that's where those debug jobs come in again. You have something to run. You think it will run well. Ask for a debug job, you get it one node, you get it for 60 minutes, you get a prompt, and run it and see if it does what you think it should supposed to be doing. It costs very little time. If it doesn't do what you think it does, and you can check its performance and see if it uses all those cores, etc. Great. Now you can build a job. If not, you see it right away. You're not wasting your time, you're not wasting anybody else's time, and you can start tweaking it. Now, the debug job runs on a compute node. So all the restrictions are there. This is why it's a good test bed. Home will be read-only. You will have no internet access in the debug job. This is on purpose. This is supposed to be as close to a environment as possible that is on the compute nodes, but interactively. Keep in mind, if it's on the GPUs, you want to test the GPUs, you first have to go to the GPU login node. So either log into Trillium-GPU, or if you're already on Trillium, you can also SSH to trig-login 01. So the G is the signage, it's a GPU node. And then you can again ask for debug node job. And this time you get one GPU, so you get a quarter node. And again, it will put you right there. Same idea of access to that one GPU, a quarter of the memory, no internet, can't write to a home or project. It's a real simulation of, it's a real case of a compute node. But that really means that you're still asking for a whole node. You're still asking for a whole GPU. You might not need that many resources. If you're just plotting, then that is definitely a bit of overkill. So we've got another service that we made, and one of the reasons we push this hard is because we know that the rest of the cluster is really for large jobs, and it's called Open on Demand. It's this deserves its own talk. In fact, if you look back on the archives, you will see James talking about Open on Demand in a colloquium in the past. But if you're doing interactive work anyway, think about plotting. A lot of that work is a lot easier if you have a graphical environment where you can, point and click. And so for a lot of the clusters, they have a feature called Jupyter Hub. So there's a Jupyter Hub associated with it where you can ask for resources, you get a job, and then it starts your Jupyter lab for you. We have something similar, but something that we consider is a bit more advanced, called Open on Demand, and it's a web-based interface for not just Jupyter Hub. So this is the address, and if you have an account on Trillium, you can log into there and work. So it has a whole bunch of applications that you can run from your browser. So you just go to your browser, you log in, and you ask, okay, I want Jupyter Lab, I want VS Code, I want RStudio, I want MATLAB, I want ParaView, I want the DDT debugger, I want to work on a terminal, I want to submit a job. It's all possible from there. And what's nice about this and why it serves a real purpose for Trillium is that you can, in fact, get a partial node. You can get a single core. You can request a certain amount of memory um, on on these nodes. You can write to home. That's actually something that you don't have in the other Jupyter hubs. Your whatever restrictions you have on compute node, like no internet access, for instance, you have internet access. So you're on your Jupyter hub. You need to pip install something, it will work. Um, Now, the only difference is, and that's why we can get away with this, is that we don't actually take resources from Trillium to do this. We have some older Niagara nodes that we repurpose for this. And so the CPUs are slightly different, but they are compatible. The GPUs are actually H100s, but they're MIG'd. So the GPUs on Open on Demand are actually a fraction of a GPU. Again, you're not running there for performance. You're running there to do some small things or some prototyping or whatever. But yeah, this is uh, a real help for all those cases where you're not running at scale, but you want to work with your data that is on Trillium. You don't want to copy it over. Um, and yeah, it's kind of nice. Any questions on that?
No questions in the chat.
Okay. Yeah. As I said, those questions should really go to James because he's the maintainer of our Open on Demand. So, yeah, you know where to find him. Yeah. So I just put that was kind of all that I had in terms of the why and how Trillium is different. I put some links on here. The first one just describes the system and also a little bit of changes from the other systems. The docs is also where all the other systems documentation is, right? We have a quick start exactly because it's a little bit different. So if you're just starting it, this is a good document to read through um, and make sure that you understand exactly what to do. If you like, or if you prefer this as a course, we have a self-paced course to intro to Trillium as well. And you can actually get a badge. That's kind of cute. That lives on our courses website. And then for Open on Demand, we also have a quick start for that, which explains a little bit better how to operate with it. But yeah, And then finally, if you need any support for working on Trillium, you can email directly to the Trillium queue in our ticketing system. So that's trillium@tech.alliancecan.ca. You can also write to support@tech.alliance.ca. So the alliancecan.ca, that's the overall support email. Eventually, it will be put in this Trillium queue. It might just take, you know, a couple hours longer for somebody to realize that it's about Trillium. So if you can, write directly to Trillium, and it'll go to uh, the right people sooner. That's all. Okay, that's it. Thank you for your attention, and if you have any more questions, I'm happy to answer them.